Patrick. As you mentioned, this is one of the most interesting thing happening in finance world as of now. So yeah, the project that we worked on was interpreting reinforcement learning trading and trading agent. And the idea was, this is reinforcement learning is something which is cutting edge these days, recently being introduced in the world of finance, and it's being used for trading and hedging. There are a couple of papers. The problem with this is just like other machine learning model, and the problem intensifies for reinforcement learning. The problem is interpretability, and that is what we focused on. And just to give you a quick introduction, I am Hariom, VP at Barclays in New York in Quantitative Analytics Division, co-authored this book called Machine Learning and Data Science in Finance, and worked on this project, or kind of guided this project with Brian and Zach. So Brian, do you want to quickly introduce yourself?
Yes, as Patrick already introduced us briefly, I'm a current student, second year at Lehigh's Masters of Financial Engineering, and in parallel work as a data scientist with the BASF Corporation.
Perfect. So yeah, what we did for this, I was saying about reinforcement learning being cutting edge, and we worked on the interpretability of reinforcement learning based trading model. We primarily focused on the visualization aspect of it. We made some kind of infrastructure or tool that can be used by traders or strats to dig deeper into what's happening in the reinforcement learning. So talking about the agenda, we will cover some basic stuff, some of the background and history. Where do we use machine learning for trading? How do we use reinforcement learning for trading? What's the need for interpretability? The approaches of interpretability, and then Brian will give a quick demo of the tool or the infrastructure that we have, followed by a couple of takeaways and future work that we are working with a couple of other students at Lehigh University. Let's move to the next one. So talking about machine learning, I think most of you might be knowing there are three kinds of machine learning: supervised, unsupervised, and reinforcement learning. And all three of it are used in finance as of now. Mostly we use like supervised learning. Supervised learning is about prediction. So there are two types of supervised learning approaches. One is classification, other one is regression. Regression, you say that, hey, what would be the Apple price tomorrow? In classification, you say whether the price will go up or down. And once you have predicted, then you use some kind of rules and make a trading strategy. That is how we use supervised learning. And unsupervised learning is looking into unstructured data, finding patterns, reducing dimension, finding clusters. And this is used as, this basically augments supervised learning when it comes to usage in trading strategy. So what we do is use dimensionality reduction. We have a lot of features, and reduce the number of features by using something like dimensionality reduction and feed it into trading mode. We do some kind of clustering and group the data and make the trading easier. So that is how we use unsupervised learning. And the most interesting one is reinforcement learning, something being used since the last couple of years. And this is more about maximizing your rewards or minimizing the punishment. So finance, if you think about it, it's mostly about maximizing the rewards in most of the cases, especially in trading, portfolio management. And reinforcement learning kind of enables trading bot, which can do trading decisions on their own without specifying any kind of rules that we do in supervised learning. Let's move to the next one. So how do we use reinforcement learning for trading? If you're not going so much deeper into theory, there are a couple of components that each reinforcement learning model has. There are observation, rewards, agent, action, and environment. So what basically happens here is the agent takes observation, performs action, and maximizes reward. As simple as that. And in terms of trading, we have a trading agent or a trader who is acting as an agent, just giving some kind of analogy how it is being used in trading. And the action can be buy, sell, and hold. It can also be like number of stocks bought or sold. You can be more complex as possible. The key thing is reward function and state variable. So you can define what you want to maximize, what you want to focus on. It can be your P&L, the profit and loss. It can be your Sharpe ratio, like risk adjusted return. It can be anything like maximum drawdown and stuff like that. Then we have state variable, which are kind of features that you put into your supervised learning models. We have stock prices as state variable, volume as state variable. And these days, we are also using sentiments as state variable for these reinforcement learning models. And environment simply can be like stock exchange. Talking about the advantages, just one more line, Brian. We'll go back to the previous one. Yeah, talking about the advantages, the key advantage here is, and that is why it's finding a lot of interest. People are finding a lot of interest in this for trading purpose. You don't have to specify any rules or strategy. When you're using supervised learning, you say that, hey, if the price goes more than 2 standard deviation, then we buy, or otherwise we sell. You don't have to do anything here. It's completely automated. And the disadvantage is, of course, the lack of interpretability. Any black box or machine learning model has that, and then a lot of data is needed. Now, this slide gives a quick overview of the deep Q learning, one of the techniques that we use for reinforcement learning. And essentially, what is happening here is, what's deep Q learning? Right? We are using deep learning for having something called Q table. Q table is a mapping of state to action, and it is some kind of neural network. Think of it like traders' brain. Over a period of time, traders, they look at the market, look at their profit and losses, and then they train themselves, and they can decide that, okay, if this is the situation in the market, whether I'm going to buy or sell. So that is what this Q table is. This is what the neural network used for this Q table is. How do we train this model? You get the state. State might be your price or volume. Then you perform an action. It can be buy, sell, or hold. On the basis of action, there will be some reward. And then on the basis of reward, whether it's positive or negative, you update the Q table or the trader's brain in the analogy here. This is the simplest explanation of one of the simple explanation of like what's happening in deep Q learning for trading for trading purpose. Now, taking a step back and looking at the bigger picture, why there is a need for interpretability in finance. And this is something which is talked about quite a lot, and it's very, very specific to finance, because in finance, you have a lot of money and reputation at stake, and small model change can lead to like big events. We have seen something like flash crash and subprime crisis in the past, but there were like models which are not designed pretty well, or there's some issue in the model, and these things happened, and there were a lot of reputation and money at risk. Then talking about the machine learning models, one thing that traders or the portfolio managers find it difficult, they find it difficult to sell it to the investors, as in they find it difficult to explain what is causing or what will lead for the model to perform well, why the model is performing well, what's the interpretability. And that's the reason we need to have some kind of interpretability for all these machine learning based models. And also, I mean, optimizing without transparency to the model becomes difficult unless and until you don't know what are the features, what is driving the model, what is causing it to perform well or perform bad. It's very difficult to optimize that. So these are the reasons for the need for interpretability for machine learning models. And I'll hand it over to you, Brian.
Hariom
Sorry.
Can you have some? I think you have some Q&A. Do you see the Q&A at the bottom, Hariom?
Can we take the Q&A in the end, because I really
of course. No, I just want to make sure you have access to it. Go ahead.
Yeah, I really want Brian to show or give the demo of the tool, which is the key meat of the presentation.
Hariom, thank you for the introduction. So kind of given the framework that Hariom has introduced, and specifically pointing to the need to easily explain exactly what's going on in these models, especially in the trading context. We can take two approaches. We have the quantitative approach, with traditional machine learning models. You've seen, Lime, SHAP values, global surrogate models, to kind of explain quantitatively what's going on, but in a very basic sense. We can just create basic plots of basically the outputs to the inputs to understand what's going on. That doesn't require any kind of complex mathematics, doesn't require any complex understanding of models. Visuals are really easy. It's the first thing we all learned in statistics or any kind of numerical course. The approach we took is visual. So the entire infrastructure that we've kind of developed revolves around the idea of plotting Q values with their respective inputs into the model. So the features, hyperparameters, and understanding in what environments of these features do certain buy-sell hold actions come out of. The next slide here, right? So why is it so difficult? As Hariom briefly mentioned, computationally taxing, reinforcement learning, unlike a simple linear model, extremely computationally taxing, using GPUs in most cases to fit these models, and the time restriction too. We can't just sit around and wait days or hours or weeks for these things to train. So ideally, we want to train it once. We want to interpret in that training during that training period and make decisions from that. There's no need to retrain. No one wants to wait again. It's expensive. Additionally, a lot of these models, especially the model that we used, these are object-oriented models when it comes to the kind of the programming of these things. It's not necessarily kind of import scikit, run 2 lines of code, and you have outputs. And so knowing exactly where to extract insights, how to store these insights while things are training is a bit of a difficulty. So there was a kind of a trial and error as to how to extract it, how to save the data, where's the data going to sit. So understanding these ideas is part of the difficulty with interpreting our reinforcement learning in general. So as briefly mentioned previously, the goal is to visualize the aspects of interpretability. So the approach here is we're going to extract the Q values that are produced during both training and testing of the model. And so kind of to get into the little bit of the infrastructure here, on the next slide, you'll see a little bit of a schematic to visually understand what's going on here, right? So we can understand the model through 3 various approaches. And this is inspired from a similar application of visual interpretation and reinforcement learning done on Atari, on the Atari game. And so there's different levels to the training. And so we start with inter-episode training, and then we go to intra-episode training, or I should say the other way around. So we start with one specific pass, then we compare between passes of data, and then obviously we have our testing. From a training perspective and a finance perspective in general, right? Training is all great and all, but how does this thing perform? What kind of insights can we derive when this model is given data it has not seen before? So a lot of the focus is on testing, but the training is equally as important to make that switch. Brief discussion about the tech stack. We use a Python backend for the algorithm itself. All the data engineering. We use the beautiful Dash framework within Python, which is built on Flask. Super easy for those of you who haven't done front-end development. And why I mentioned the importance of Dash. Ideally, this is given an infrastructure like this would be given to a trader who is monitoring these reinforcement-based strategies. And having a beautiful front end where you can just point and click rather than look through, massive data frames or go into databases, it's just not clean. So a front end on this, and we'll have a demonstration of the front end here on the next slide, makes it super easy. We use the BigQuery database, free, easy, integrates well with Python, and we'll use the Google Colab GPU, super accessible if you haven't used it before. Great piece of technology that's widely available, and I think it's free to use. So as I mentioned, the structure of the modules is very simple. We have one RL interp application that basically pulls on these four different separate modules, as I briefly mentioned here. We have testing, we have inter episode, and then we have our data engineering and our database structures floating around on the back end to make things super easy. We use these databases rather than just saving into pure CSV files, just to make it computationally organized and efficient. We can have 30 episodes. We can have 120 episodes. You don't want to have 120 CSV files. It doesn't really flow well. So for our case study, we use Vanguard's ETF, market ETF. Again, nothing specific, just to have something that's physically traded as opposed to an index. And we use data between 2017 and the end of 2018 to avoid COVID mess. Again, these are just arbitrary kind of figures just to feed data into the algorithm so we can begin to create these visualizations. And so specifically for features, we'll use the price and volume change as our state variables to feed into our algorithm, so we can begin to learn the environment given these two. And so we'll explore the following hyperparameters as you all see on your screen here. And the problem statement, as I mentioned, right? Can we use heat maps? Can we plot features versus their trading decision to derive interpretation? In other words, are there certain patterns of buy, sell, hold in bear markets versus bull markets? Is there a certain volume change in a day that gives certain buy, sell, hold signals from our algorithm? And with these ideas, right, we can begin to answer, why did the algorithm buy on a certain day? Why did it sell on a certain day? And the answers are in these visuals. So we'll start with the demo, and we'll kind of walk through the various modules. And you all see sort of what exactly this may look like to the trader at the end of the day on the front end. So as I briefly mentioned, you have your three modules at the top here. We have kind of a training. We have the testing training, and then the two training, the inter episode and the intra episode. And so a trader would easily be able to switch between tabs as need be. So we'll start with the intra episode understanding, right? And so in the visual you all see here, right? This would be kind of the evolution of the average price change when the algorithm buys, sells, and holds on the given episode. So on the y-axis, you have the average price change in a given episode for a certain action. And as you can see, for example, for buying, you would expect, assuming kind of a long-only strategy, buy low, sell high, you would expect over time that the algorithm would begin to decrease. We'll go back here, apologies. You'd expect that the average buy value would decrease. And as you can see here, over time, it begins to decrease. And eventually you want that to go negative, and you want your sell to obviously go positive to generate alpha here. And so here as well, so within a specific training episode, we develop Q value plots, right? So what are the Q values over time? What do they look like in a specific episode? And as you can see here, the Dash infrastructure makes it super easy to switch between these analyses. And then obviously with the Plotly, with the Plotly library, you have these hover over points. So the trader would have easy access into what exact Q values are occurring on certain days for certain values. And as you just saw there, you're able to zoom in and make, and the user is able to make quick and easy, extract quick and easy points of information that he or she may need while kind of analyzing these things. In addition to the Q value plots, as you see here, the dropdown gives me four options, similar to the state variables, as I mentioned earlier. You have a table, you have graphs, and now we'll get to the heat map, which is really what's of interest. So again, here we'll talk about the heat map when you get to the testing. But here, as I mentioned earlier, you know, the average price we can plot this over time within an episode itself, or the price, the physical price change within the episode itself. And as you can see here, you'll see all the actions that are occurring in a specific episode with the respective price change on the y-axis. And again, we expect that over time, as we slide the episode as we go from episode 1 to 10, you expect the buys to be negative, you expect the sells to be positive, and so on. And you can see this evolution over time is really where we're going. And so similar to understanding evolution over time, within this specific DQN strategy, we have something called an epsilon greedy strategy. We'll have something called an epsilon greedy, where the algorithm will take a random, absolutely random decision, and we would hope that over time, as the algorithm begins to understand what's going on in its environment, these values, the amount of epsilon greedy decisions would decrease. And so we'll see here that in the pie chart under the state delta tables, we're going to hope that as the episodes increase, the amount of greedy decisions decreases. And as you see here, and it'll live update, you'll see all this begin to decrease over time. And so we started with, I think it was like more than 20 on the first episode. We're down to 2 in the 8th, and so on until we get to 0. So these are just more graphs. Let's get to the heat table. So the heat map. So this is really what's important. As you see here, we have the the volume change. So our features will be on the axes, and then our actions will fill in our heat map. So the reds will be our sells, and the ones will be our buys in the algorithm, right? And so as we set our conditions here on the left-hand side, we can begin to analyze that, right? Is there a pattern of price change and volume change that leads to a certain action, a certain patch of red, a certain patch of blue? And from here, obviously, we can begin to change hyperparameters. In this case, we have to just change data sets. But in essence, what we did was we took a bunch of different hyperparameters, fitted the model, tested it on a bunch of different hyperparameters, and we just produced different data sets. In practice, right, this would be tested all in like a live environment with the algorithm, hopefully changing kind of in a go live basis. But in essence, as we can see here, right, this patch of red is a certain combination of price and volume. This big blue area, combination of price and volume. And so we can begin to understand, right, hopefully, again, buy lowing, we hope to buy low and sell high, and we can use this exact heat map to derive these insights very clearly. So the takeaways here from that heat map, extremely sensitive to the number of layers in the deep neural net that fit its Q values. As we kind of just saw, played around with, visual interpretation allows for easy confirmation of, is our algorithm doing what our strategy should be doing? Are we buying low, selling high? And are the intended effects of hyperparameter changes doing what they should? Is a change in the discount factor resulting in what should happen? And with that, kind of as Harry mentioned, further work, and I briefly already hit on this. Ideally, we would be able to use that facade or that front end to make changes in our model. So on a trading desk, maybe the trader would be able to make changes to kind of a dummy data set and see what happens, not necessarily go live with the algorithm, but see what happens with the model as we change hyperparameters and tune it. Obviously incorporating more features, technical indicators, sentiment data, kind of integrate NLP and reinforcement learning together. And then obviously, aside from the visual, incorporate the quantitative approach. How does the neural network specifically affect the estimated Q values, which is kind of our decision engine of buying, selling, and holding. And obviously interpreting those Q value calculations as much as we can. With that said, I guess we'll turn our attention to the questions. And then kind of hand it back over to Professor Zorro.
Thank you, Brian. That was great. So just to summarize, what we have done is we have tried to dig down deeper into what's happening in the reinforcement learning based trading, which is something people find it difficult these days. It's easier or not easier. I mean, there are a lot of techniques for supervised and unsupervised learning, sharp line, but reinforcement learning, which is something new. And that is what Zach and Brian have done in this project. So let's move to Q&A. I can see. So first question is, using RL, can we also keep the objective function as conditional value at risk and minimize that? Yes, of course you can. And you can use whatever metric you want to. Actually, there's a paper called Deep Hedging, in which there's this reinforcement learning based hedging technique. There they use conditional CVAR, actually, conditional value at risk. So you can refer to that paper and see how it is being used. I don't know whether you're also asking about portfolio optimization. So definitely, I mean, it can be used for portfolio hedging, it can be used for portfolio optimization. The problem statement remains same. You just have to design your reward function accordingly. Brian, you have anything to add? Feel free to add.
What was the frequency of the data sampling and what was the expected time horizon of the investment decisions? So the frequency of the data daily, and the expected time horizon of the investment decisions. So I'm hinting that that's sort of like a train test split question. I think we used 80% of our data on the training, 20% of it on the out of sample testing. Factor execution was not necessarily in the original development of the specific visualizations that you saw, right? Completely arbitrary factors, completely arbitrary data points, horizons. It's more of the infrastructure, right? Is there an easy way to extract these things? So for sure, yes. Execution can be another factor. Execution cost can be another factor that's added in kind of in the future, along with kind of the technical indicators and the sentiment stuff that was mentioned earlier.
Mm-hmm. There's another question by Siddharth. It's asking when to use daily data versus high frequency and how do they affect the ML model. I mean, you can use both kind of data, daily data, high frequency data, but and the good thing is, I mean, the positive thing about machine learning is the more the data, the better it is. I mean, if you don't have a significant amount of data, it's better to stick to like statistical model or the simple model. But I guess your high frequency data or like daily data, machine learning model can be used. It's preferred. Now, the things that you have to be careful about is number one, overfitting. At times, what might happen is if you're using a lot of data, there might be a chance of overfitting, and that there are a lot of tools and ways to avoid that. There might be like another issue of non-stationarity or I mean, generally what the asset class data are non-stationary. And if you're using it in machine learning models, you have to be careful. A lot of machine learning models, they can take non-stationary data. But yeah, I mean, you have to be careful before using the non-stationary data for all these machine learning models. Then there's another question by Marlon. I'm not sure whether I'm pronouncing the name correctly. The question is, was this strategy tested with multiple assets? If so, how do you aggregate signals? Otherwise, please share your thoughts on generalization. I guess as of now, correct me if I'm wrong, Brad, I guess it was used for just one asset. It can easily be extended to multiple assets. You just have to add more features. And as Brian mentioned, there are a couple of few things we are thinking in terms of future work. We are thinking of adding like sentiment data as well. So it would be pretty interesting to see NLP and reinforcement learning work together. You can aggregate signals. You can like throw in whatever state variable or feature you want to in all these models. Just have to be careful about all these points that I mentioned, non-stationarity and overfitting. And actually for some of the portfolio optimization case or the usage of portfolio reinforcement learning in portfolio optimization, I've seen multiple assets, the volume data and the historical prices of multiple assets being used in reinforcement learning kind of models. So yes, you can have multiple assets and many signals.